So we sort of did the first three chapters on last week. And gee, I only have to put like another 6 chapters into today. So yeah, so obviously you're going to have to go kind of quickly. But you can, from what we've been doing the last week or so, you can see how bonding and shape are really important into all the other stuff we've learned about intermolecular forces. So hopefully this will just sort of be a brief reminder of how these two things are related. So let's just go remember when we looked back at the periodic table. Atomic size increased as the number of shells increases, and that makes sense, right? Every time we add a new shell, it's the principal quantum number, the shell number goes up. Obviously, we add a whole new shell of electrons, atomic size gets bigger. The thing that maybe wasn't quite so obvious is as the nucleus gets bigger and bigger, it pulls on those electrons more and more. So as we go across the periodic table, we've added a new shell. Remember when we go down one, we add a new shell. But then as we go across, we're adding more electrons, yes, but they're not getting any further away. And at the same time, we're increasing the size of the nucleus. We're adding more positive charge. And so that's pulling on those electrons and pulling them closer and closer and closer. So actually the atomic size goes down as the atom itself adds to the number of protons. So the atomic size increases as you go down, but then it decreases as you go across. And we can see this just with looking at the sort of periodicity. And you remember why it's called the periodic table, because so many of the chemical structures and properties are periodic. They change as you go across or up and down. And one of the most dramatic is that every time here you add a new shell here and here and here. We're just adding 1 to the number of shells, and you can see how they jump up in size. And it kind of nicely explains how it's much easier for these particular elements to lose that 1 electron so easily. And these, if you remember, are anyone tell me which group this is? Lithium, sodium, potassium. Which group is that? It's even given right here, group 1. Which group is that? It's very distinct of elements.
Metal.
There are metals. They're a specific kind. Remember, these are the ones when you throw them into water, they blow up. You really, really, really want to give that 1 electron away and become positively charged. Do anyone remember what they're called?
Alkali?
There you go, alkali metals. Yeah, alkali. So you generally will, why they're called alkali metals, a lot of times you will find them with a hydroxide, like, NaOH, KOH, because OH likes to be negatively charged, and these atoms like to be positively charged. So they make a nice couple. Oh. So how you can tell that these things are easily ionized, this gives you an idea of how many electrons are in the outermost shell. And this is the ionization energy. If you remember, the ionization energy is the amount of energy it takes to remove an electron. And this is beryllium. Beryllium has 4 electrons. And you can see from here, the first two, really easy to remove. See, it takes only 0.9 kilojoules per mole to get rid of the first one. Second one, only 1.76, so slightly less than twice as much. But then to get rid of that third one is a huge amount of energy is required for that. And that's the difference between these being valence electrons, which are relatively easy to remove, and this one being a core electron. And so if you ever look at a table that lists these ionization energies, it's pretty easy to determine how many valence electrons versus core electrons it has, because the amount of energy will be small, 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 and then spike way up. Once it spikes like that, these are going to be valence electrons, and these are going to be core electrons. And it also has to do with the size. Once you've removed the valence electrons, once you've moved all the valence electrons, that basically means that that last shell has been removed. So that now that atom gets much, much, much smaller. Because it gets much smaller, the force of the nucleus pulling in on it, and remember, that was our effective, the effective energy of the nucleus goes way up once we've removed all the outer electrons and are just left with the cores. And here's just gives you an idea how that works. So if we look at lithium, for instance, lithium's only got 3 electrons here. If we remove one of them, the outermost one, very, very easy to do. And then you're left with lithium plus, which is a very stable ion. That next one, much more difficult. And the third one, very, very difficult indeed. When we go down to sodium down here at the bottom, which is another alkali metal, again, that first one, easy to remove. And then a big jump for the second one. And so we can see that this sort of tells us how big the atom is and tells us how many electrons are core versus how many are valence. Yeah. So let's just look at metals really, really quickly. I'll just give you some of the differences of properties between metals and nonmetals. Then we talked a little bit about this before. So you remember, obviously metals, generally shiny solids with relatively high melting points. They're good conductors of heat and electricity, and they're malleable. You can pound them, you can shape them into different shapes. They tend to lose electrons and form cations. Pretty much all metals do that. In other words, they're easily oxidized. And you remember the difference between oxidation and reduction. Oxidation means you have electrons taken away from you and you become more positive. And that's what metals like to do. And reduction is when you have electrons added to you and you take on more negative charge. And because metals are easily oxidized, it means they give their electrons away. That means they're strong reducing agents. In the presence of metals, the metals get oxidized, and whatever's in the presence of metals gets reduced. That's what being a reducing agent means. It means it allows reduction of something else. And so when we have, let's say, for instance, we have metal, and with water, the water will get reduced, the metal will get oxidized. That's what happens to your car bumper. So most metals will form oxides, which are basic when you have them in aqueous solution. Here. And you get more and more metallic, the more and more electrons you get as you go down. So as you go down, you're adding more and more electrons, obviously it becomes much more easy to lose one. If you've got 80 electrons, it's much easier to lose one than when you only have 3. So you get more and more metallic behavior as you get larger. And as you go from right to left, you get more metallic also, because obviously everything over here is not a metal at all. Those are all the non-metals, right? And then on the staircase here, we have the metalloids, which have properties sort of in between. They're semiconductors like silicon. So they conduct electricity, but not terribly well. And then as you move more and more to the left, become more and more metallic. So just, yeah, quickly, just to go over the metals and non-metals again. Generally, non-metals are going to be smaller than metals. And that makes sense because as we're moving to the right, excuse me, remember that the atoms are getting smaller and smaller because of the size of the nucleus keeps getting larger and larger. So the Z effective, or the relative charge of the nucleus, gets greater as you go to the right. So the ionization energy also gets higher for nonmetals. It's much easier to take electrons away from metals because basically they're more stable as positive ions. It's much more easy for them to lose electrons and become positively charged than nonmetals. It's very difficult to take electrons away from nonmetals because they are much closer to the happy place, to the electronic nirvana, where you have 8 electrons in your outermost shell. They're really close to getting there. And so it's much more stable for them to gain electrons and then become like a noble gas configuration. So different types of chemical bonding. This also comes into the kind of intermolecular forces these different types of molecules will be able to have. So ionic bonding, remember, always a metal, usually it says here, pretty much always a metal and a non-metal. And it involves the transfer of electrons, and that is key. One element gets an electron and it keeps it. The other element loses an electron and doesn't get it back. And it's that positive and negative charge that keep them stuck together. But remember, covalent is when you share those electrons. They may not always be shared equally, of course, and that's super important for polarity and a whole bunch of other intermolecular forces. You share electrons, usually with 2 nonmetals, almost always 2 nonmetals, because they don't form ions when they're together because they have similar electronegativities, if we remember what electronegativity means. Anyone give me a quick definition of electronegativity? You're still awake. What's electronegativity? If you remember, metals have low electronegativity. Non-metals have high electronegativity. What does that mean? Kind of important. You can tell me about electronegativity.
It's kind of like the ability for the atom to like pull the electrons towards it.
Exactly. Great, Kyle. Yeah, that's exactly it. If I have a metal, if I have 2 elements, X and Y, and one pulls on those, and they're sharing an electron. So you remember a chemical bond, a covalent chemical bond, is a pair of electrons, and they're sharing them. And if Y has a higher electronegativity, those electrons are going to spend more time close to Y. And that gives us a dipole. Remember, a dipole is when you have an unequal sharing of electrons, so that there's more density around Y and less density around X. And so X has a partial positive charge and Y has a partial negative charge, because those electrons spend a little more time closer to Y, and that gives you a dipole, and that leads to polarity. And then finally, metallic bonding is sort of different than either one, because basically they're sharing electrons throughout in the entire piece of metal. It's not just two atoms sharing electrons, it's all the atoms sharing electrons. And so basically there's just positive charges stacked on top of each other and negative charges flowing in between them. That's why metals are such great conductors of electricity, because they have all these free electrons that are just moving back and forth. And all you have to do is just put a little bit of charge on one side. The electrons will immediately move from the negative side to the positive side. And that's why they conduct electricity so well, because they have all these electrons that are moving around anyway. So these are the different, it's just a review of the different types. First of all, ionic. We've got, like I said, we've got electrons being transferred. The sodium gives that electron to the chlorine, and the sodium stays positive and the chlorine stays negative. And so here you can see the sodium atom gets much, much smaller now that it's lost its outermost electron. And so basically a whole shell is gone. And so it's much smaller. And the chlorine gets somewhat bigger. And so when they make this ionic solid, you can see these little sodium atoms and these big chlorine atoms forming this lattice that they'll stack on top of each other. Now, when you have covalent bonding, you have two different nonmetals, and they share that pair of electrons and stay close to each other because they're sharing that electron. So they have to stay close together in space so that pair of electrons is shared. And here in the metallic bonding, you have all these positive metallic ions and this sort of what we call a sea of electrons sort of swimming all in between them. So at any one time, the atoms are not charged, but as they move around, you can see that you can easily have ions forming instantaneously anywhere in here. So that's why the electrons move so quickly and conduct electricity so well. And then here's our electronegativity that Kyle showed you he is an expert at. So electronegativity just means, as he said, the ability to pull electrons toward oneself when you're in a bond. And that's the key part, when you're in a bond. And Linus Pauling came up with this about, like 80, almost 70 years ago now. And there's no units, it's just a number. And the number goes from a low down here for cesium at 0.7 and a high of fluorine at 4. Now you don't have to memorize this, but one thing you probably should remember, the three highest electronegativities are nitrogen, oxygen, and fluorine. Chlorine's close. I think if nitrogen's is slightly more electronegative than chlorine. And remember, these are the three elements that do what? These three elements have something in common: nitrogen, oxygen, and fluorine. What do they do?
Bond?
Elements don't. Which one?
Hydrogen bonds, is that
Exactly. Hydrogen bonds. So they form hydrogen bonds because when they are covalently bound to hydrogen, they cause such a partial positive charge on hydrogen that it forms a very stable interaction with another fluorine. It leads to these really high partial negatives and partial positive charges coming together, which leads to a very stable interaction between that high partial positive and high partial negative charge. That leads to a very, very stable interaction. And nitrogen, oxygen, and fluorine can do that. Chlorine is close to being able to do that, but not quite. So it doesn't really form hydrogen bond. It forms very stable polar-polar, dipole-dipole interactions, but it doesn't really form hydrogen bonds like nitrogen, oxygen, and fluorine can. So if you remember anything, just remember it's these three, super, super important. And it's the difference in the electronegativity between one atom and another atom, which determines whether it's ionic or covalent. And then if it's a big, big difference, I mean, it's a really tiny difference in electronegativity, it's a non-polar covalent. And if it's a big difference, it's polar covalent. And if it's a huge difference, it's ionic. I'll go into that. Show you the table now. So remember, these are the three. We have a pure ionic, which is the most polar you can get because we have an actual charge, physical charge, positive and negative. Polar covalent, large difference in electronegativity. And pure covalent, complete sharing. So the electron density around each atom is about the same. So that it isn't polar at all. But when we look at the differences, it will tell us whether or not we have non-polar covalent, polar covalent, or ionic. And it's sort of on a gradient. Around 1.7 or so in difference, it's really kind of hard to tell the difference between an extremely polar covalent bond and an ionic one. The difference becomes so great that this ionization or this difference in charge becomes so great that it becomes pretty much covalent, pretty much ionic. When you're dealing, generally you need a metal and a non-metal to get this much of a difference, and that's when you that's when you go from extremely polar covalent bond to an ionic bond. And then down here, non-polar covalent. This will happen, of course, if you have two atoms that are exactly the same. That's by definition non-polar covalent because they have exactly the same electronegativity. So my size of my electron cloud here is going to be exactly the same as the size of my electron cloud here. And so no ability to be polar. Now remember, polar and polarizable are two different things. And when we got into intermolecular forces, remember, if we have a really big electron cloud here and a really big electron cloud here, it's kind of easy in the presence of like a charge, for instance, to push the electron cloud in one direction or another. Like for instance, if I have a positive charge here, if I have like a sodium ion, for instance, it will pull this electron cloud toward itself because it's positively charged, and it will make a slight dipole. This chlorine will be slightly more negative, and this chlorine will be slightly more positive. And so anyone remember what this is called? When we have a non-polar molecule being induced to become slightly polar in the presence of an ion. You remember what that one was called? This is the very last chapter. We just dealt with this like a week or two ago. The induced kind of gives it away. I'll even give you the first two parts. It's an ion-induced something.
Dipole?
Yeah, exactly. It's an ion-induced dipole. It is a kind of, it's a way of sort of basically forcing polarity when there wasn't any before. when chlorine and chlorine were just hanging out together, just being all chill, they were completely nonpolar. In the presence of something that's charged or very highly polar, it can be induced to become slightly more polar than it was before. See, it's all together, man. It's all one part of something. So remember, we did pick polar bonds. We make this arrow sort of the little cross in it, indicating that this is where the partial positive charge is, because it has a little positive shape there. And this is where the partial negative charge is. And you can also do it this way. Remember that this symbol means partial. Lowercase delta means partial. Uppercase delta means change. So they're kind of similar in that regard, because we have a change to a slightly positive and a change to a slightly negative charge there. So either one is fine to do. Now, oh boy, electron dot symbols. Basically, if you remember how we did these, I'm going to go through these fairly quickly. We just used the number of valence electrons and presented them as dots. And so if it had, for the metals, if just basically whatever charge they were going to become, we put those number of dots. So for instance, sodium has 1 electron in its outermost shell, so we just gave it 1 dot, and then it would lose that to another molecule. So electron dot structures of ionic compounds were pretty easy to do, because they always lost and gained the same number of electrons. For covalent compounds, it was a little trickier. So nitrogen here has 5. And remember, we would go around for nitrogen when we would go 1, 2, 3, 4, and then 5. And the reason we did it that way was because each we want to see how these electrons are going to be shared. And so remember, if we have a lone pair, that generally is kept by the atom, and these electrons that are all by themselves become bonds. So 1, 2, 3. Nitrogen has 3 bonds and 1 lone pair. It has 5 electrons, 5 valence electrons. And the same is true for oxygen. We would go 1, 2, 3, 4, 5, 6 valence electrons, because it's in group 6. It would keep this lone pair, and make 1, 2 bonds. And so it was an easy way to sort of see, based on the number of valence electrons an element has, how many lone pairs is it going to have, how many bonds is it going to make. And like, carbon, 1, 2, 3, 4. It doesn't have any lone pairs and makes 1, 2, 3, 4 bonds. So it's an easy way to sort of remember how that worked. So if you're going to make multiple bonds, remember you could change a lone pair on a surrounding atom and make another bond. For instance, if I have, let's just give you an example. Like here, we've got oxygen, ozone. We've got 3 oxygens. So if we write the number of valence electrons, each one is going to have 6, right? So we've got 2, 4, 5, 6 for this one. 1, 2, 3, 4, 5 for this one. 1, 2, 3, 4, 5, 6, 7 for this one. So the problem, so we've got 18, we got our 18 valence electrons. The problem is this one has a positive charge, and this has a negative charge. And so we write a resonance structure because this structure is possible, or this structure is possible, just by moving that pair of electrons to one side. So it's the same Lewis structure for the same molecule. But you remember that neither one of these is exactly accurate, because what happens in reality is that we have a bond and a half. And we remember this sort of led us to bond order, whereas we looked at the number of bonds here. This had 2, this had 1. We added them together and divided by 2, so the bond order was 1.5. But remember, when you do these resonance structures, you try and make the best structure you can and see if there's another way to do it. And a lot of times, there's 2, sometimes even 3 different ways to do these. And then, like I said, this shows you the actual structure of ozone. Looks like this, so that each has the right number of electrons. And we know scientifically, we know by measuring these bond lengths and bond angles that it looks like this. It's bent, and these bond lengths are exactly the same, meaning that this one bond here, this is bond 1 on this side, and this is bond 2 on the other side. One isn't a single and one isn't a double. They're in between. They're about, like I said, a bond order about 1.5, because these bond lengths and angles are exactly the same. And that wouldn't be true if one was a single bond and one is a double bond. Anyone remember the difference in length between a single bond and a double bond? If I have, let's say, a carbon-carbon bond here, single bond and a carbon-carbon double bond, which one's longer?
Someone say it's single bond.
It is, you're right, it's single bond. Because in order to get another pair of electrons to be shared, the atoms have to come a little bit closer together in order to get the shape right. And a triple bond is even shorter.
Shorter than a double bond.
Yeah, so, okay. Try and keep moving here. So, yeah, one important thing when we're doing these types of representations, these Lewis dot structures, there's going to be exceptions to having 8 electrons, right? Because one thing we're always trying to do when we're writing these structures is we want to give everybody 8 valence electrons. That's why when we write nitrogen like this, with 1, 2, 3, 4, 5 valence electrons, what nitrogen basically wants at the end of the day is to have 8 electrons. So when it makes the 1, 2, 3 bonds, then it has 2, 4, 6, 8 total electrons, both to itself and shared. Same with oxygen. It's sharing 4 electrons, and it keeps 4 electrons to itself, so it has a total of 8. But that's not always going to be the case, because we know that some electrons either have some elements either have more than 8 electrons in the outermost shell, and some have less. So, for instance, beryllium and boron. Beryllium only has 4 electrons, or only has 2. Sorry, it only has 2 valence electrons, and then two core electrons for a total of 4. It only has 2 valence electrons. Boron only has 3. And so basically it shares all the valence electrons it has and then doesn't have any more. So it's beryllium's only going to form 2 bonds, and boron's only going to form 3, and that's fine. That's all the space for that's all the electrons they have. Sometimes you're going to have odd numbers of electrons, and we call those radicals. Remember, when you have just one sort of unpaired electron, it's called a free radical, and these things are extremely chemically active. Like that's why hydrogen peroxide is such a efficient method to like kill bacteria and other things. It's because peroxide looks like this. And then it has that 1 electron. So oxygen has that 1 unpaired electron, and so it makes it really chemically active. It goes around trying to grab another electron from basically anything, and it's very, very strong. This is because oxygen is so electronegative. When it wants an electron, it's going to get it, and so basically it just goes around stealing electrons from like a whole bunch of different things, and breaks down cell walls and blows up DNA and everything else. So that's why it's so active. Now, the other exception to the octet rule is when you have more than 8 valence electrons in your outermost shell. And these things happen for nonmetals. Now, whoops, let me go back for a second. For nonmetals, and what's really important to remember, from period 3 or higher. And the reason for that is when you're in period 1, what's the subshell that's available to you in period 1? So if n is 1, remember these are going back to our quantum numbers. If n is 1, what can L be, the subshell? If I have an n of 1, what is my L? The subshell. So n is the shell, L is the subshell. What subshell is available when I'm in period 1? Man, you guys have been studying, right? Period 1. So I got 1 shell
It's,
number, first one.
so L would be n minus 1.
Right, n minus 1. That's right. So what subshell is that? So if L equals so L would equal 0. And what subshell is that?
So I'm gonna say
That'd be
1s.
1s, exactly.
yeah, 1s.
1s. So I've only got room for 2 electrons. That's it. So that only has hydrogen and helium. That's it, right? Those are the only 2 elements in period 1. They only have either 1 electron or 2. That's it. Once we go to the second shell, what can L be? So when n equals 2, what is L?
P.
L can be, yeah, we can have P or, well, and what else? So if that,
S.
or S, right. So L can be either 0 or 1. So 2 has S and P for a total of how many electrons? If I have 2S and 2P, how many electrons is that total? I know I can put 2 in S. How many can I put in P?
Be like 8.
8, exactly. I can put 6 more in P. So that's a total of 8. So any element in period 2 has room for 8 electrons. Fine. But that's it. I can't put any more. Like for carbon, oxygen, fluorine, nitrogen. can't put any more than 8 electrons. It's impossible because there's no place to put them. We've only got 2s and 2p. But when I go to period 3 here, now I've got 3s, 3p, and what else?
D.
D. I finally have d orbitals now. So when I'm in period 3, I got room for lots more electrons now because I've got 2 in s, 6 in p, and how many in d? Anyone remember?
10.
10, right.
10, yeah.
That's a total of 18. So, I mean, there's space for 18 valence electrons. I mean, you're not going to have that many, but there's room for them. And so you can have, so for instance here, phosphorus, how many valence electrons does phosphorus have in that particular model? I've got phosphorus pentachloride. How many valence electrons does phosphorus have there?
Someone said 5.
Yes, 5 valence electrons, and how many total?
40.
And that's in the whole molecule. How many electrons is phosphorus both? So it has 5 valence electrons. How many total electrons does it have there?
$30.
Just the phosphorus.
Oh. Got, let's see, 10?
10, right. Because there's 2 here, 2 here, 2 there, 2 there, 2 there for a total of 10.
Right.
See, more than 8. What about the sulfur here? That's sulfuric acid. How many electrons, how many total electrons does sulfur have in that model?
Looks like 12.
12. Yeah, it's got 2 for each, it's got 4 from each of these double bonds. And then 2 more here and 2 more there for a total of 12. And sulfur does that a lot. So basically, if you get a test and with these sort of, and you're looking to make these Lewis structures and you see phosphorus or sulfur there, you know there's going to be something tricky. Because a lot of times sulfur will have 12 electrons and phosphorus will have 10. So let's look at some shapes. So all the things, the shapes that we learned about had everything to do with how electrons repel each other. That was the sort of the key thing. So remember, electrons are negatively charged. So they like to sort of place themselves as far as possible from all the others. So if I have carbon with 4 hydrogens around it, each one of those bonds, remember, is a pair of electrons. And since they're negatively charged, these are going to want to space themselves as far from each other as they possibly can because they're negatively charged. And so in that instance, remember, it forms sort of this tetrahedral structure. It looks like that, remember? I can't really draw it. But it forms a tetrahedron. If it had 3 bonds, like boron, the greatest distance between these is a plane with 120 degrees in between them. That's as far apart as those 3 things can get. So it forms a planar triangular planar. So single bond, double bond, triple bond, they all count as a sort of a single group of electrons because they're sort of in the same area in space and they want to get as far away from each other as they possibly can. That's basically the really easy way to sort of figure out what's going on. That's all VSEPR means, is that electrons want to be far apart. That's it. And these were some of the shapes they took. So if there's only 2 places for electrons, the furthest apart from each other is 180 degrees on a plane. So these can't be any further away from each other than that shape. And the same is true here. I remember I just did with like boron, you will see this because it forms three bonds. Tetrahedral for 4, and this sort of trigonal bipyramidal for 5, because this is the farthest away 5 can get. The farthest away 6 can get is sort of an octahedral shape. And so to remember these things, we sort of had this sort of general rule. A, X, M, E, M, where A was the central atom, X is how many surrounding atoms does it have around it, how many it's bonded to, and then E was the number of lone pairs that it had. And then you'd figure out, like for instance, ammonia, NH3. So it's got 2 lone pairs on the nitrogen, shared pair there, shared pair there. You'd say, okay, A is a central atom. It's got 3 surrounding atoms, 1, 2, 3. And it's got 1 lone pair. So it's AX3E, and you just look up what shape is AX3E. You can be able to do that on the test as well, obviously. You just look these things up. And then these are the different shapes. What I do want you to remember is some of the factors that affect the angles. So remember, lone pairs means there's no atom at the end. So there's nothing here with a positive charge on it that lowers the sort of basic, the amount of charge here. If I have an atom here with positive charges in the nucleus, that charge is going to be slightly less, right? So it's not going to be as strongly negative. If I don't have any atom there, it's basically just two electrons. I have a full 2 charge of -2. That pushes other electrons away even more strongly. And so it increases the distance between the lone pair and the bonded pair. It moves them further away. And so it also reduces this other bond. It reduces this other bond angle because they're both pushed further away from the lone pair. And double bonds, same thing. I've got more electrons in the similar space. More electrons means higher density of negative charge. So I've got more negative charge here. And so it pushes these other atoms further and further away. And so reduces this bond angle slightly. I'm just going to skip through here and get to polarity. Polarity is sort of big for intermolecular forces. So remember, you can have, so polarity, all polarity means, bond polarity is what's the difference in electronegativity between atom A and atom B. That's all bond polarity means. So remember, if it's more than about 0.4, it becomes polar. And if it's more than about 1.6 or so, it becomes ionic. So that the more and more, the larger and larger difference in the electronegativity, the more and more polar it is. But the overall polarity of the molecule depends on how these are organized. So you can have polar bonds and a nonpolar molecule if individual bond dipoles cancel or don't cancel. And what that means is, like for instance, if I've got carbon dioxide, I've got a dipole pointing in this direction because oxygen is a lot more electronegative than carbon. But I also have another dipole pointing in exactly the opposite direction. It's the same size and it's exactly the opposite direction, so they cancel each other out. So I have 2 polar bonds in a non-polar molecule. So you have to remember that it's the polarity of the bonds and the shape that determine whether or not a molecule is polar. So here, well, here's the exact thing. I've got two polar bonds and a net dipole moment of 0 because they're exactly the same size, going exactly opposite directions. If, however, I've got two polar bonds in water, but the shape determines its polarity because it's not, I have a dipole pointing in this direction and another dipole pointing in this direction. So they're pointing in opposite directions, but not completely opposite. So they're both pointing in the same direction, but not completely level with each other. So if I add them together, I get a net dipole moment pointing up, and it's more than 0. So I have two polar bonds and I have a polar molecule because they're pointing in the same in the same direction and not canceling each other out. And it's all because of these two lone pairs of electrons on the oxygen that actually physically take up space, and we have to account for them. So that's why when you're drawing these things, you have to remember about the lone pairs. So I'm going to skip this because we didn't really spend a whole lot of time on hybrid orbitals. I do want you to remember hybrid orbitals because it made a big difference when we were talking about how many electrons and the different types of bonds that are formed. Some of these, so you remember, we can have sp, sp2, and sp3, and it depends on how many bonds are formed. So with BCl2, it has 3. Remember, beryllium has 2 electrons. It has 1 in S, and it needs to form 2 bonds. And so it sort of hybridizes, and both bonds have the same energy. So it hybridizes an S and a P and forms this sp orbital. Because in the 2s, the 2s is full. And so it's really not going to share either one of those electrons, and it forms 2 bonds of the same energy. So what happens is it pushes both those electrons into p orbitals and hybridizes the energy so that they're the same. So now I have 2 sp orbitals, both with a single electron in them, which need to be filled, remember. So one is going to go in here, one is going to go in there. And they have the same energy. So they're hybridized, form 2 bonds, and so they're S and P. And then when we form 3 bonds, or we need 3 spaces to put electrons, like in boron, forms 3 bonds of exactly the same energy and orientation. It takes 2 of the electrons that it has in S and 1 that it has in P, and mixes them together to form 3 hybridized sp2. So we get this from the number of electrons, sp2. So there's 3 electrons, so it's sp2. It's going to form 3 bonds. It's not because there's, also because there's 1 S involved and 2 P's involved. So 1 S and 2 P's. for a total of 3 electrons, 3 places to put electrons. Now let's go to when we need 4. And when we need 4, now we're going to need the 1s and all 3 of the p's for a total of 4 different orbitals, each with 1 electron in them. So now we have s and 1s and 3 different p's. So sp3 also tells us how many electrons are involved. We just add these numbers together. 1s, 3 p's, that's 4. 4 electrons, 4 bonds. 1, 2, 3, 4. And it gives us the tetrahedral shape as well. But what if we need 5? Now, once we get into 5, that means we're adding d orbitals, because we've run out of orbitals. I've got 1s, I've got 3 p's, and that's 4. That's it. Oh, wait, no, now I've got d's I can add. So 1, oops. Now I can add 1 more. I got 1, 2, 3, 4, 5. That's when I need 5 bonds. And that's why you need to get to the third shell. You need to get to an N of 3. You need to get to the third shell, because now I've got S, P, and D available. So 1, 2, 3, 4, 5. And it's 1s, I got my 3 p's and 1 d. And I just add them together. I got 1, 3, and 1. That's 5 electrons. So 5 electrons, 5 shared electrons, 5 different bonds. And so phosphorus here has 5 different bonds. So it's a way to remember that. So types of covalent bonds, just remember, first bond is always what we call sigma. And that's sort of the easiest, that's one of the easier ways for electrons to be shared. It's just the overlap of orbitals. If I've got 2 hydrogens, I've got the 1s and the 1s, each with 1 electron in it, they overlap a little bit and share that electron. That's a sigma bond. Now a pi bond is any subsequent sharing of electrons between the same 2 atoms. And I think we've learned that carbon is a common one, oxygen, nitrogen forms 3 bonds. So the first one is always sigma, and the second one is always a pi bond. And you remember that pi bonds have a really weird shape. So I've got the sigma here is a shared pair that come in close contact. So these come in close contact with each other and overlap. But remember, the pi bond was really weird because it had an electron up here, an electron over here. So basically it had electron density above and electron density below. So above here and below. And remember, when we added another bond, then we had electron density in front and electron density behind. And when you have a pi bond, it basically locks everything into place. Because remember, when you built the models in the lab, when you had sigma bonds, you could move them, right? You could just twist them around. That was just fine. But once you had a double bond, they're locked. You could move them around, but you couldn't, they were sort of locked in place. Because once they're sharing electrons above and below, they're sort of, they can't move. If you move them, they're not sharing those electrons anymore. So let's just quickly go through 6 and then we'll sort of call it a day. Any questions so far? I know I'm going super fast. But I sort of just want to briefly touch on a lot of different things. This one should be fairly simple because we just sort of did this recently, and it's just basically how to do calculations. There's not a whole lot of theory involved. Just good old stoichiometry. So when you're going to be balancing chemical equations, I guess you have to be, get used to that idea. You're going to be given questions where either you're going to have to make up, you're going to have to, I'll give you the equation and you're going to have to balance it. Or it'll be something like, oh, quiet, Jerome. Or I'll give you something like this. Magnesium and oxygen gas react to give magnesium oxide. You're going to have to know that magnesium is a metal and it's just magnesium atom by itself, solid, plus oxygen. You're going to have to remember, and somebody must have delivered something. Jerome. So you have to remember that oxygen is O2, not O, and it's a gas. And then arrow, because it's a reaction, and magnesium oxide. So you're going to have to remember that magnesium is +2 when it forms an ion, and oxygen is O2. It's O, -2. Then you're going to have to realize that, oh, right, I need to balance this. There's 2 oxygens here, so this has to be 2. Now I need 2 magnesiums for every 1 molecule of oxygen. So adjust the coefficients, make sure that everything's balanced. And then also, when it says specify the states of matter, that's going to be important when you're doing the energetics, like when you're doing Hess's law. Because maybe in Hess's law, one of the reactions has oxygen as a gas, maybe has oxygen as a liquid if it's really, really cold. You're going to have to take that into consideration when you're looking at the energies involved. So take all these into consideration. Sometimes you're going to have to translate a statement into actual chemicals. You're going to have to remember the formulas. You can't change the formula. The formula, it is what it is. It's MgO. It ain't anything else. So that will lead you to have to balance the equation. So the number of atoms have to be the same on both sides. And this is going to be super important. Remember what a limiting reactant is. You're not always going to have enough of each reactant for them to be used up completely. There's going to be more of one and less of the other. And so whatever one is left, that's going to limit the amount of product. That's limiting reactant. So be sure when you're doing this, take into account the number of moles of each one that's available. Like in the last one, we had 2 moles of magnesium for every 1 mole of O2. So just because, if I had 1.5 times more moles of magnesium than oxygen, doesn't mean that oxygen now is limiting. It isn't. It means magnesium is limiting because I need 2 moles of it for every 1 mole. So don't just assume that because I have more of one thing than another, that the thing I have more of is limiting. It's not always true. What you need to do is work out exactly how much product you could make. If I had so much magnesium, how much product could I make? If I had this much oxygen, how much product can I make? Whatever one is smaller, that's your limiting reactant. And then to figure out what's the excess is, use up, once you figured out which one's limiting, you figure out how much product is being made. When you figure out how much product is being made, how much of the excess reactant is left over. Use up all of the limiting reactant. How much of the excess reactant was used in making that much product? Use that up, whatever's left over, that'll be the excess reactant left over. Jesus. Shh, guys. All right. So determination of empirical formulas. This, we sort of did this early on. And the easiest way was to do this was to take percent composition, like if it was, whoops, go back. if it was, for Christ's sake, if it was like, say, 80% carbon, 20% hydrogen, we would say, okay, how am I going to figure out what the formula of that compound is? I would take that percent, remember, and change it to grams. So in other words, if I had 100 grams of this stuff, whatever it is, 80 grams of it would be carbon, and 20 grams of it would be hydrogen. And then, because grams don't really mean anything in chemistry, you need moles, right? So then I would figure out, well, I've got each mole of carbon weighs 12 grams, each mole of hydrogen weighs 1. So I would have 80 divided by 12 moles of carbon, 20 divided by 1 moles of hydrogen, and then figure out figure out how many moles of each one I had, and then try and get it to the smallest whole number ratio. Now, molarity. Molarity is going to be super, super important when you're doing reactions in liquids, in solutions. And why molarity is so important, because we're using moles when we do, hey guys, we use moles when we're dealing with reactions. And when we're in solutions, molarity tells us how many moles we have. It's the number of moles of whatever it is we have dissolved in our solution in a liter. So when we're dealing with like milliliters, for instance, remember that's 1,000th of a liter. That tells us how many moles we have in each one. So then I can compare and compare how many moles of each reactant I have. When I dilute something, sometimes when I make a solution, it's going to be too concentrated for what I need it for. It's going to have way too much in it, and so it's not convenient to measure out really, really, really small volumes. It's really hard. You probably learned that in the lab. Remember, you're trying to measure out 1 milliliter of something. And that's hard to do accurately. What's much easier to do is measure out 100 milliliters. That's a lot easier to do. So what I'll do in that situation is dilute my solution. So I'll have, and when I dilute the solution, remember that the number of moles I had before and after are going to be the same. The only difference is going to be the volume. So if I take 1 liter of something that's 1 molar, that means I have 1 mole of it. If I dilute that to 100 liters, at the same number of moles, I just have a higher number of liters. So I've just changed the concentration from 1 to 0.01. It's exactly 100 less. But the number of moles is always, always the same. So it's really easy to do dilution because the number of moles are going to be the same. So my concentration times the original volume is always going to equal the concentration times the second volume, because this is moles on this side, and this is moles on this side. So you're going to have to do some of these dilutions. And just remember that the number of moles is always going to be the same. So just a couple more things, and then we'll call it a day. These are just different ways of expressing concentration. One, it's just the mass percentage. When we have really low concentrations of things, generally we'll go to how much mass there is of something in the total mass solution. Like for instance, like a percent glucose in a hospital solution. They don't give it in molarity, they'll give it in percent. So they'll just take the number of grams of glucose glucose in the total mass of the solution. So let's say a liter will be slightly more than a kilogram because it's got, salt and glucose and a whole bunch of other stuff dissolved in it. Let's say it's like 1,050 grams. So if I had 50 grams of glucose and 1,050 grams of solution times 100 would be my mass percentage, my percent mass of glucose, okay? Now, if instead of, what if I have a solution? What if I have a liquid dissolved in another liquid? Much easier way to express that would be volume percentage. And you see that with everyone's looking for isopropyl alcohol to make, hand sanitizer, right? You want to look for something with a high volume percentage. All that means is what's my volume of isopropanol? How much alcohol do I have? And I remember alcohol is a liquid, so I just measure it in volume. So if I have 80 milliliters of isopropyl alcohol and 100 milliliters of solution, I got 80% isopropyl alcohol. That's all that means. It doesn't take the density or anything into consideration. It just takes how much volume did I have before, how much volume do I have after, and then that's the percent. All right, so we didn't quite get to the last thing on thermodynamics. We're going to do some of that this afternoon. Looking at thermodynamics, we're going to need to remember Hess's law. We're going to need to remember the volumes of Q and some calorimetry, and then that's about it. So we'll sort of review some of that this afternoon.